All right, friends, let's get started. Today we're going to deal with carbohydrate metabolism. We're going to start glycolysis, and you'll see how we get from glucose all the way to hopefully acetyl-CoA. We probably won't get quite that far today, but we'll get through most of glycolysis. That'll link us up with triglyceride metabolism, and then we'll do the citric acid cycle, probably finishing up with that on Wednesday. So the first step of glycolysis is modification of glucose on the C6 hydroxyl to form a phosphoester. You use ATP to do this. This is massively downhill in energy, irreversible, because you're converting a level 1 reactivity phosphoanhydride to level 2 phosphoester. And so it's quite favorable and downhill. A glucose molecule, having gone through this step, is committed. The enzyme is called hexokinase. Kinases, as you know, transfer phosphate groups, the gamma phosphoryl group from ATP to usually an alcohol on some group. And yeah, that was it. I won't show you the mechanism because you've seen a kinase mechanism before in some of the earlier stuff we did with triglyceride metabolism. We would just draw the same thing, only using glucose 6-phosphate. The glucose is the nucleophile with the C6 hydroxyl group. Okay, the second step is an isomerization step. We're going to convert glucose 6-phosphate into an isomer of glucose. We're going to convert it into fructose 6-phosphate. So fructose differs from glucose in an interesting way. So let me draw the structure of fructose for you. So this is fructose 6-phosphate. And I'll number the carbons real quickly so that you can see which carbon in glucose becomes which carbon in fructose. Okay. Notice that the stereochemistry at C3, C4, and C5 is still the same. Up, down, up versus up, down, up. We're drawing the 5-membered ring in this weird sort of way. We're not attempting to really draw a chair. 5-membered rings don't adopt chairs. Their conformations are a little bit more flexible. Looking at the difference, where is the hemiacetal carbon on glucose? Which carbon is it? That was not rhetorical. Somebody say something. C1, right? That's the hemiacetal carbon, or the carbonyl carbon. Where is it on fructose? Numero dos. Good. If we opened up the ring, glucose would be what kind of carbonyl compound? Hemiacetals open up and they form either aldehydes or ketones. So what would glucose be? Aldehyde, right? How about fructose? Ketone. All right, let's draw those ring open forms. I'm not going to, and we'll just draw them in the shape that resembles where they're at now. I'm not going to draw the ring opening mechanism. You've seen that before and should be able to do it. Glucose becomes an aldehyde. Oops. Whereas if fructose were to open up, here I'm going to call this ring closing because we'll be going forward from glucose to fructose. But I'll draw the ring opened form of fructose. Would indeed be a ketone. C2 is going to be the one that's the carbonyl. So you can see that fructose 6-phosphate is a ketone. Now, you might think to convert between one and the other, it would be convenient to reduce the aldehyde on C1 to an alcohol, and then subsequently oxidize the alcohol on C2 to a ketone. But it turns out you don't need to do that. You don't need any oxidizing or reducing reagents for this process. You only need proton transfer. And I'll show you how this works. It's really kind of cool. What we're going to do is do keto-enol tautomerization. Now, you've seen that before a ton of times. You know that each ketone or aldehyde has a less stable enol form, because carbon-carbon pi bonds are less stable than carbon-oxygen pi bonds. And to get from the keto form to the enol form, you simply need to deprotonate on the alpha carbon and then reprotonate on the carbonyl oxygen. So back in the day when we were drawing this mechanism, we'd first deprotonate on the alpha carbon to show a negatively charged enolate intermediate. We would remind ourselves that that negatively charged enolate intermediate the charge was delocalized on both the alpha carbon and the carbonyl oxygen, and to get to the enol, we just needed to protonate on the oxygen. Is that sounding familiar? What we're going to do instead in the enzyme active site is we're going to take care of all of that at once without an intermediate. So here's removing the proton. Here's forming the carbon-carbon pi bond. We would normally have put a negative charge on either the alpha carbon or the carbonyl oxygen. Instead, we're going to show that carbonyl oxygen getting protonated by an acidic group in the enzyme active site to get the enol intermediate. And that enol intermediate's going to look like this. Now, as I'm drawing it, someone asked in the 9 o'clock hour, is the stereochemistry of that enol intermediate important? And I said, no, it's not gonna. So I don't actually know whether the two OHs are cis versus trans to each other. It ends up not mattering at all because the enol isn't a product of the reaction. So this is our enol intermediate, only this is not just one enol. The enol we just made is here. And from the perspective of what used to be C1, we would have called C1 the carbonyl carbon and this the alpha carbon. But from the perspective of the OH group on C2, this could be the carbonyl carbon and this could be the alpha carbon. The thing about the enediol intermediate is it's the enol of two different molecules. It's the enol of the aldehyde, but it's also the enol of the ketone. So to get from the enediol to the other ketone is just another proton transfer step. We'll have a base from the enzyme active site, remove the proton from the C2 hydroxyl group. Electrons will kick down to form a pi bond, and then we'll protonate on the orange alpha carbon, and that's going to get us to fructose. Two different tautomerization steps via this enediol intermediate. I want you to pay attention to this because nature is going to do this again in this same pathway. Anytime you have an alpha hydroxy carbonyl compound, you can tautomerize via an enediol intermediate to move the carbonyl over one and then move the OH group over the other way. So a convenient way to swap between two things. Now this step is reversible. The free energy change isn't a big deal. The enzyme that does this is called glucose 6-phosphate isomerase, meaning it is an enzyme that catalyzes an isomerization reaction. All right, questions about that? Okay, let's keep going. You'll see very soon why nature wanted to move the carbonyl carbon over one. All right, let's do step 3. Step 3 is another irreversible kinase step. you're going to take fructose 6-phosphate as the starting material, and you're going to invest another molecule of ATP. So you expect the enzyme that catalyzes this reaction to be a kinase, and it is. Again, you're going to be converting a less stable phosphoanhydride here into a more stable phosphoester here. So you expect the reaction to be quite downhill to a more stable phosphoester here. So you expect this reaction to be quite downhill in energy. The new phosphoryl group, the gamma phosphoryl group on ATP, ends up on C1 as a phosphoester. And then, of course, we still have the C6 phosphoester as well. This product is called fructose 1,6-bisphosphate. Why don't they say diphosphate? Well, diphosphate's reserved for an actual phosphoanhydride connection between two phosphate groups, as in ADP. They call it bisphosphate to indicate two phosphoesters on two different oxygens in the molecule. So again, you're converting a less stable phosphoanhydride to a more stable phosphoester. That's quite downhill in energy. The free energy change in the cell is about 4.5 kilocalories per mole. It's essentially irreversible. All right. And again, I won't show you the mechanism there because that's a kinase step, and you've already seen that mechanism. Pay attention to the fact that nature puts phosphates on 1 and 6. There's a certain amount of symmetry there, and actually you're going to see that in the next step. All right. So, step 4 begins with fructose 1,6-bisphosphate. We're going to first ring open that up. And I won't show you the mechanism for ring opening because you already know it. But let's just draw the resulting product. Now, oops, sorry, there's a phosphate group on C1. And let's number the atoms 3, 4, 5, and 6. Now, the enzyme, this reaction is totally reversible. The enzyme that catalyzes it is called aldolase. But in the forward reaction, it's going to do a retroaldol reaction. So, remember what an aldol reaction is? That was the distant past. If you don't, that's probably a good thing to review. The aldol reaction is a reaction between an enolate and a carbonyl. And the product of an aldol reaction is a beta-hydroxy carbonyl compound. So a retroaldol would start with a beta-hydroxy carbonyl compound and go back to the enolate and the carbonyl. So let's see if we can, if we're going to do in the forward direction a retroaldol reaction, let's see if we can identify the beta-hydroxy carbonyl compound here. So here's the carbonyl carbon at C2. Here's the alpha carbon. Here's the beta carbon. If we were going to do a retroaldol reaction, which bond are we going to break?
3 and 4.
Bond between 3 and 4, or the bond between the alpha carbon and the beta carbon. And just by the way, here is the beta-hydroxy carbonyl functional group that is an aldol product. Notice how doing the retroaldol reaction at this time would split the molecule up into a 1, 2, 3 carbon piece and another 1, 2, 3 carbon piece. We'll draw what those products are, but even for right now, we can pause and go back to the structure of glucose and ask, why didn't nature do this on glucose? And I think that's instructive. Here's glucose in its ring open form. Glucose also has a carbonyl carbon, an alpha carbon, and a beta carbon. If you were to do, and there's an OH group on that beta carbon, so glucose is also a beta hydroxycarbonyl compound. If you were to do the retroaldol reaction on glucose, how many carbons would end up on either side? 2 on here, right? Because you break the bond between alpha and beta, and then 4 over here. Now maybe that's not such a bad idea, but the 2 sides would be different enough that you might need different enzymes to process them. You're going to see pretty soon that because we move the carbonyl over 1, we can convert via a retroaldol reaction into 2, 3 carbon pieces. And you'll later see those 2, 3 carbon pieces are not identical, but they are interchangeable via a very, very simple reaction. So there's chemical logic going on here, and as I've said before, if you have eyes to see, you can see the hand of God in it, because it just makes sense, and it's really efficient. Let's slide that carbonyl over to get it in the right spot to do a retroaldol that can split this molecule into 2 equal parts. All right, so here's how we would, I'll talk you through how we would normally show the mechanism for a retroaldol reaction, and then I'll show you how we'll do it abbreviated for an enzyme. We would normally, in a retroaldol reaction, deprotonate the beta hydroxy group to get a negatively charged intermediate. Then electrons would kick down to form a carbon-oxygen pi bond here, and these electrons in the bond between beta and alpha would break and would go onto the alpha carbon as an enolate, and then we would protonate on the alpha carbon to get to a neutral starting material. We're going to do all of those things in the same enzyme catalyzed step in the active site. We're going to deprotonate, make the carbonyl, break the bond between alpha and beta carbons, and instead of making an enolate on the alpha carbon, we're simply going to protonate on the alpha carbon. And that's going to generate our products, which are 2. The first product from C1, 2, and 3 is one that you've seen before because it was a product that we got from the metabolism of glycerol, from triglyceride metabolism. This is C1, C2, and C3 of fructose. And this molecule is called dihydroxyacetone phosphate. And then the remaining carbons, C4, 5, and 6, are going to be this aldehyde. I'll continue to number them here, 4, 5, and 6, with a phosphate group on C6. And this is called glyceraldehyde 3-phosphate. Sorry, the missionary's calling, and I meant to, it's P Day, and my missionary in Kentucky is calling. I meant to click X, and I clicked check mark on Facebook Messenger, so there he was. He tells me he misses his chemistry classes. I'm not sure if he's just flattering me or what. He hasn't taken my class. He took Chem 105 and 106 last year, and I think he said it was kind of rough, but he learned a lot. So anyway, where are we? All right. So the retroaldol reaction. Questions about that? Yeah.
With regards to the lines between the different reactions, you do have to open the ring for the all aldolase to then get to these two?
Yes, because without opening the ring, you don't have a ketone.
So it's aldolase that is the enzyme that's doing this.
Aldolase is doing all of it. Or I actually don't know that. I don't know whether fructose 1,6-bisphosphate binds in its ring open form and then opens, or whether it has to open before it binds the enzyme. That's an interesting question that I don't know the answer to. The ring opens, and then the retroaldol reaction happens. Yep. Okay, others? All right, now, look at those two products that we just got. They're two 3-carbon units. They both have phosphate groups on it, so they're similar. But similar is not good enough. Ideally, we'd like them to be the same thing so that we can use the same enzyme machinery from that point on to metabolize both sides. You've seen a similar situation before, just today. Glucose and fructose were different in that there was an aldehyde on C1 in glucose, but a ketone on C2 in fructose. Same situation here, an aldehyde on the first carbon of glyceraldehyde 3-phosphate, a ketone on the second carbon of dihydroxyacetone phosphate. Before we interchange them via tautomerization, we're going to do that again here, and it's going to be via an ene-diol intermediate. So you'll see nature works by patterns, uses similar mechanisms in similar situations. Step 5 is going to be the conversion of dihydroxyacetone phosphate into glyceraldehyde 3-phosphate. After step 5, we will have made 2 molecules of glyceraldehyde 3-phosphate for every molecule of glucose that we started with. This step is reversible, and the enzyme that catalyzes it is called triose phosphate isomerase, and sometimes people call it TIM for short. So TIM is the most efficient, one of the most efficient enzymes ever. People call it a perfect enzyme. If you look at its kinetics, it's so fast that it's almost diffusion limited. So what that means, you'll learn about it in biochemistry, but it takes molecules a while to bump around in water and find each other. The fastest enzyme is limited by the fact that you still have to wait for molecules to diffuse in water. And TIM is so fast that really water diffusion is almost the slow step. So it's a really interesting enzyme, works really efficiently, but we're going to see that it follows that same pattern of tautomerization to get an ene-diol intermediate, and then tautomerization in the other direction to get the aldehyde. So the base from the enzyme, a base from the enzyme active site, deprotonates dihydroxyacetone phosphate alpha to the carbonyl, where the hydroxy group is, and then we would make an enolate, and then that enolate gets protonated on the carbonyl oxygen to give you the enol. We'll show that tautomerization all happening at once. Here is the ene-diol intermediate that forms as a result. And again, we've got this same situation where relative to the ketone, pink, we've got the enol from the original ketone, but in a similar way, this hydroxy group is attached to what could be a carbonyl carbon, and the carbon adjacent to that could be an alpha carbon as well. In other words, this ene-diol intermediate is the enol of 2 different molecules. To get to the aldehyde, we simply deprotonate on the orange oxygen, and we protonate on the orange alpha carbon. And that gives you glyceraldehyde 3-phosphate, again, by a tautomerization step. Notice that, and I can erase the numbers here, notice that the stereochemistry of this hydroxyl group is set in this step where we protonate the orange alpha carbon, and the enzyme preferentially protonates from a specific side of that ene-diol so you get the correct stereochemistry of that alcohol. So we now have two equivalents of dihydroxyacetone phosphate. We have this, two equivalents of glyceraldehyde phosphate. We have this one that we formed in the retroaldol reaction, and then we have the second that we formed in the triose phosphate isomerase step. So everything we do from here on out, step 6 through 10, is going to happen twice. And you'll need to remember that as we try to balance things out and figure exactly how much energy we're getting out of this. Okay, questions so far? Okay. All right. So let's now begin with step 6, and this is a payoff step. Step 6 is going to happen twice. Everything from 6 through 10 is going to happen twice. And in this step, we're going to pay off our original debt of ATP. So in step 6, we start with glyceraldehyde 3-phosphate. And we're going to end up with this molecule that's called 3-phosphoglycerate. I'm sorry, I'm conflating two steps in my mind. Sorry about that. We're going to end up with this intermediate, which is called 1,3-bisphosphoglycerate. Okay, so this reaction is reversible, and one of the reasons you can tell that it's reversible is we're starting with an aldehyde, which we said was sort of level 1, very reactive, and we're making, over to the right, an acyl phosphate, which is also level 1 reactivity. So we go from one kind of highly reactive carbonyl compound to another, and therefore it shouldn't be a surprise that that can happen in a reversible way. The reagents for the reaction, you can see we've oxidized. We've gone from the aldehyde oxidation state where we have 2 carbon-oxygen bonds to, at the first carbon, the carboxylic acid oxidation state where we have 3 carbon-oxygen bonds. And this enzyme, because it's an oxidation, it's going to use a molecule of NAD+, and it's going to generate NADH, and then a proton will need to be removed. Another ingredient to the reaction is inorganic phosphate, or PI. You'll see what that is in a little bit. That's how biochemists abbreviate it. That's where the phosphate group comes from. The enzyme that catalyzes this reaction is called glyceraldehyde 3-phosphate dehydrogenase. And it's called a dehydrogenase because it's an oxidation enzyme that removes a hydride in blue and then a proton in green from the molecule. This enzyme sometimes gets abbreviated in your biochemistry text as GAPDH, and you may hear about that. It's a pretty ubiquitously expressed enzyme in nature. All right, so let's talk about the mechanism of this one. It's kind of interesting. An active site cysteine residue in the enzyme, so remember the side chain of cysteine is just a thiol, attacks the carbonyl carbon of the aldehyde. Probably the enzyme deprotonates the cysteine as it is attacking. So we'll have some base in the enzyme remove a proton from the cysteine, at the same time as it's attacking the carbonyl carbon of the aldehyde. And we'll show the enzyme protonating the tetrahedral intermediate as an alcohol. One of the things that enzymes do to accelerate reactions is they protonate charged species so that you don't have to go as uphill in energy when you're doing a step. So let's draw what that intermediate would look like. We've got an OH group on what I'm now calling C1. We have a sulfur from the enzyme, the cysteine residue, and then also on C1 is the hydrogen from the aldehyde. On C2 you've got the OH group, and then C3 has the phosphoester. What we're ready for now is the oxidation step. So we're going to position Na, and you've seen this type of oxidations before, so it shouldn't be a surprise. We're going to position NADH very close, NAD plus, very close to the substrate. The enzyme is going to remove the proton from the alcohol of this intermediate. Electrons will kick down and the hydride will get delivered to NAD plus in the usual way. By the way, this intermediate looks like a hemiacetal, only the OR group is a thiol instead of an alcohol, so we call it a hemithioacetal. But when that reaction happens, it oxidizes the hemithioacetal to the oxidation state of thioester. And then, of course, you get NADH out. Now, thioesters are also level 1 reactivity. That's why it's not a big uphill in energy to go from the aldehyde to the thioester. But now you can see what we're set up to do to get from the thioester to the acyl phosphate. All we need is a nucleophilic acyl substitution reaction. And I'll draw you the first step of that, except I can't write substitution. And then I'll let you fill in the details from there. This is when our molecule of inorganic phosphate, I'll just draw phosphoric acid as it would appear at pH 7, will attack the carbonyl carbon to generate a tetrahedral intermediate, and then I presume you can draw that tetrahedral intermediate and show the thiol getting kicked off, and that would give you the acyl phosphate. Okay, so that's step 6, one of the more complicated steps in glycolysis. But you can see what we're sort of trying to do here. If we ever want to recover ATP, we need to convert a phosphate group into something that has a decent leaving group attached to it. And as we look at 1,3-bisphosphoglycerate, look at what that phosphate group is attached to. Over here, a carboxylate. Carboxylate's level 4, very stable, decent leaving group. So we're set up now after this GAP-DH step with a phosphate that is bonded to a good leaving group. This phosphate is now primed to become the gamma phosphate of ATP. All right, so in the next step, we will take 1,3-bisphosphoglycerate, and in this next step, we're going to totally recover our investment of ATP, remembering that step 7 happens twice, because for every molecule of glucose, we get 2 molecules of glyceraldehyde. So in this reaction, we're actually using ADP as a nucleophile. It's going to attack the gamma phosphate group of 1,3-bisphosphoglycerate, and that's going to generate a new molecule of ATP, And that happens twice, so we've totally paid off our debt. The product of that reaction is going to be what you would expect, the leaving group, 3-phosphoglycerate. And notice that this reaction starts with an acyl phosphate, that's still level 1, and as a product you get ATP, which has a phosphoanhydride in it, also level 1. So this reaction is reversible. And because it's reversible, the enzyme here is actually named for the backwards reaction. This enzyme is called phosphoglycerate kinase, named for the backwards reaction. So I'll just show you briefly how this happens. I'll draw ADP here for you. And the beta phosphoryl group is going to act as a nucleophile. It's going to attack the acyl phosphate on the phosphorus side of ADP. You're going to get a pentavalent intermediate on that phosphate, where the phosphorus is attached to 5 things, ADP on one side, and then the phosphoglycerate on the other side. Electrons from one of the negatively charged oxygens will kick down and kick off phosphoglycerate as the leaving group. The acyl phosphate from our starting material becomes the gamma phosphoryl group of ATP. All right, so far about glycolysis, it's been about dividing the molecule into 2 equal parts, and then oxidation and functional group manipulation so we can get a phosphate in just the right spot where it's attached to a good leaving group and it can be attacked by ADP to generate ATP. This reaction that we've just talked about is sometimes called substrate level phosphorylation, meaning we phosphorylate ADP to get ATP, but we don't do it with the ATP synthase from the electron transport chain. We get the phosphate group from an enzyme substrate. That's why it's called substrate level phosphorylation. All right, questions about that? Yeah.
Are the errors from like the oxygen off the phosphoglycerates, are those like reversible or are those
Oh, the reaction, the whole reaction is reversible. Yeah. Yep. Okay, others? All right. So let's talk about step 8. Oh, and I need a 2- on that.
What's covering the string down top?
Right, just the point that ATP has a phosphoanhydride bond, whereas the starting material has an acyl phosphate bond, and those are similar. Yeah.
So the creation of the carboxylate is more stable than the ATP is reactive, and that's why we go forward, or is it just the opposite?
So the question is, your question is, why are we going forward if this is reversible? And let me look. The free energy of this step is actually 0. So that means the forward rate is exactly the same as the reverse rate. You'll see when you get in biochemistry, nature does also gluconeogenesis. Sometimes it needs to transport glucose from one part of your body to another, and so sometimes it will actually run the backwards reaction. It will use the glycolysis enzymes that are reversible for a lot of those reactions. It can't use the irreversible ones, so it has to have a different pathway for those ones. Yeah?
I suppose if we're getting rid of the product that's coming from this completely reversible reaction, then the Chapter's principle will drive it forward, right?
Right. If we're getting rid of this, consuming this in the next reaction, then Le Chatelier's principle will drive it forward. Exactly. Yep. All right. Good. So let's do step 8. it turns out that right now, this phosphate group that's in 3-phosphoglycerate, we're also going to want to do a substrate level phosphorylation with that. The big problem is that right now that's a phosphoester, level 2 reactivity. And we want to do a reaction that will generate ATP without a lot of trouble. We want it to be downhill in direction. So we need to change where that phosphate group is and change its surroundings to make it as good of to put it in as good of a situation as we can possibly engineer so that ADP can attack it and there can be a good leaving group on the other side. Right now it's not in a good spot. So step 8 of glycolysis is going to be to move the phosphate group in 3-phosphoglycerate to move it over a carbon to the 2' or to the 2C2 hydroxyl group. So here's 3-phosphoglycerate. What we're going to make is instead 2-phosphoglycerate, where the phosphoester is with the C2 hydroxyl instead of the C3 hydroxyl. The enzyme that catalyzes this reaction is called mutase, and I'm going to tell you don't worry about the mechanism. It's simple enough, but it involves an intermediate that you're not necessarily familiar with, and I decided it wasn't worth the trouble. If you want to know about it, come talk to me. Basically, in the enzyme active site, there's a histidine side chain where one of the imidazole nitrogens is bonded to a phosphate group. That's a weird functional group that's about the same level of reactivity as an acyl phosphate. It ends up phosphorylating the C2 hydroxyl first, and then the resulting histidine leaving group comes in and attacks the phosphate group here to remove it from the C3 group. Again, probably not worth our time to worry about it, but if you want to come see it or talk through it, we can. So what do you think that does? Well, it moves a phosphate group, which has a lot of negative charge, one atom closer to the carboxylic acid group. So there's probably a buildup of some charge repulsion there. The carboxylate's negatively charged, the phosphate group's negatively charged. There's probably some charge repulsion there. Let's talk about the other steps that happen. We'll do step 9. And step 9 is an elimination reaction. So we're going to take this molecule that's called 2-phosphoglycerate. And we're going to take, and remember this also, everything from step 6 on happens twice. We're going to do an elimination reaction that's going to remove the proton alpha to the carboxylate. At the same time, electrons are going to kick down to form a pi bond, and at the same time, hydroxide's going to leave, but it's going to get protonated by the enzyme as it leaves to help it leave. As you know, hydroxide is a not good leaving group. So it's no surprise that the enzyme has to protonate it so it can leave. So we lose water. This is an elimination type reaction. And the product is this. Oops. Why not? Called phosphoenol pyruvate. And the enzyme that does this is called enolase. So for you to understand the name of this enzyme, first I should draw for you what pyruvate is. Pyruvate is this ketone, right? The enol of pyruvate would look like this. and then it's phosphoenol pyruvate, because the OH of the enol is now a phosphoester. Okay. Questions about that elimination reaction? All right, and
Wait,
go ahead.
so I guess how do we switch email to pyruvate?
So we haven't done that yet. This is the product, phosphoenol pyruvate. I was just telling you where the name comes from. Pyruvate is this alpha keto acid. Pyruvate enol is the enol form, and then if you put a phosphate group on it, it's phosphoenol pyruvate. All right, now we are set up, though it's not immediately obvious, we are set up to have this phosphate group become the gamma phosphoryl group of ATP. It doesn't really look like we should be in that situation here. The last time we did this, we had an acyl phosphate. Here we've got a phosphoester, and phosphoesters are only level 1 reactivity. So what's going on there? And it turns out that part of it is the charge repulsion between part of the reason this phosphoester is especially high in energy is the charge repulsion between the carboxylate and the phosphate. But the other part is the idea that the leaving group, if you think of a nucleophile coming in and what would get kicked off on the other side, it's an enol that could rapidly tautomerize to a ketone, and enols are less stable, whereas ketones are more stable. So embedded in this phosphoester is a leaving group that can leave as something that can immediately convert into something more stable. So between the charge repulsion and the enol-keto difference in energy, this molecule is actually pretty high in energy, pretty reactive, and it turns out it's going to be very downhill in energy for ATP to form. So let's show you how that happens. This is the final step of glycolysis. We didn't get to it in the 9 o'clock hour. Those folks were like, make it stop, so I had mercy on them in step 8, and we called it good. But you guys are all sitting quietly taking notes, by which I assume that you're fine, so we're just going to continue. All right, here's phosphoenol pyruvate. Phosphoenol pyruvate. The enzyme that catalyzes this reaction is named for the reverse reaction, even though this reaction is irreversible. I didn't make it up, you're right, and I don't have the delta G on this one, but this is strongly downhill. It's thought that what happens is that the enzyme protonates.
Why are we losing it?
Sorry, I was doing this backwards. It is strongly downhill, but we're going to use ADP to generate ATP. All right. So it's thought that what happens is that the enzyme protonates the alkene at the less substituted carbon. Now, all of this appears to happen in the same step, so we're just going to talk through it. But if we drew the intermediate from this first step, where would the positive charge be? Would it be on C2 or C3? C2, because if it's there, it can at least be stabilized by resonance with the carbonyl oxygen, right? Now imagine that as an intermediate. A carbon-oxygen pi bond here with a positive charge on that oxygen. Does that give you a sense for why that phosphorus is really reactive? Because what can be kicked off is just a neutral ketone. So what we're going to show is in the same step, the oxygen from ADP is going to attack the phosphoryl group. You know what? Stay tuned on that. We'll have to pick that up next time. I wasn't quite where I wanted to be. So